Welcome back, folks. We're going to look at Norton's theorem now. You're going to be really good at this. It's going to go a lot quicker than Thevenin's theorem because you already know how to do it. You just don't know you know how to do it. So we're going to revisit the very first problem that we looked at for Thevenin's theorem. And if I recall correctly, we used a 5 ohm load resistor for it. So let's get that up here. All right. There it is. And I pulled a random number, but I want to use the same random number. So is that random anymore? I don't know. As we did before, so maybe the answers line up. So we've got 5 ohms for RL, and we still have the same fixed circuit. So this is the circuit that I did like 5 or 6 videos on as I was introducing how to find Thevenin's theorem. For Norton's theorem, same kind of 2 goofy steps. Find I Norton, find R Norton. That's really all we got to do because we want to get this down to a Norton equivalent, which is going to be a current supply with a parallel resistance, and then we hook up the load out here. So we've got to figure out what I Norton is, and we've got to figure out what R Norton is. So let's do it. So find I Norton for starters. And believe it or not, you've already done this. You just didn't know you did it. Okay. For a different circuit, not for this one. So let's start with our circuit like this. And to find I Norton, we start by finding the short circuit current. All right. Find it however you want. Okay, I'm going to use mesh. I'm going to use the shortcut. It's going to be a 2x2. There's no current supplies, so it's all KVLs. We got I1 touches a total of 9. It shares 6 with I2. I2 shares 6 with I1. And it touches a total of 11. Oh no, maybe we did find. Oh, we didn't. We did this. All right, it's all coming back to me. Is it coming back to you? You can go flip back through the videos. We go up 12 and we go up 0 for I1 and I2. So that's the mesh shortcut. For that, we just got to find the solution. We did this when I was introducing method number 2 for finding the Thevenin resistance. All right. So from that we find I1 is 2.095 amps and I2 is 1.143 amps. Hey, that sounds familiar. Okay, so let me store those. And look, I1 doesn't touch I short circuit, I2 does, and it goes in the positive direction. So I short circuit is simply I2, 1.143 amps. All right, stand back. The relationship between I Norton and I short circuit, they're the same. Okay, just like V open circuit and V Thevenin are the same, I Norton and I short circuit are the same. Okay. All right, so there's the first part. Not too bad, and we already did it. That's why I'm saying learning Norton once you know Thevenin is super quick. Okay, oh, that was all behind my head. Let's get that up there. All right. Now find... Next step, find R Norton. And here's what I'm going to tell you about this one. R Norton is related to R Thevenin. In fact, they're the same. Okay, so if you can find R Thevenin, you already know R Norton. So R Norton equals R Thevenin. Use previous methods. So I don't need to go through introducing them all. We've been practicing it already. Use previous methods. Okay, so I'll do it here because I can do it fairly quick. Okay, let's do method 1. There are no dependent supplies. So we replace the independent supplies with their ideal resistances. Now we have a better understanding of why that's the ideal resistance. And then we find our Norton looking back into the circuit from the terminals where the load will connect. Okay. Just like before, our Norton is 3 in parallel with 6, and all of that is in series with 5. 3 in parallel with 6 is 2. Add 5 to it and you get 7. Okay, that's it. We found the Norton equivalent, or we found the information we need for the Norton equivalent. Let's draw it. Let's draw it. Okay, so here's your current supply with a parallel resistance. This is going to be 7 ohms. This is going to be 1.143 amps. Alright, and then we're going to hook up the load. There's the load. And to make it consistent with the example I did before, let's make it 5 ohms. Right, this is our load. And what we were interested in is the voltage across the load, right, and the current through the load. This one shows up everywhere too because look, it's a current divider. And because it's a current divider, I'm just going to use that current divider, that formula, to say that 1.143 amps splits according to the ratio. I need the opposite branch resistance, so that's going to be 7 over 7 plus 5. Okay, so we get 7/12 of that current. So let me go ahead and do that. 7 divided by 12 times 1.143, and that gives us 2/3. That feels familiar. I think I recorded that video 1 or 2 days ago. That number feels familiar. Okay, 2/3 of an amp. 2/3 of an amp flowing through a 5 ohm resistor. We can say the voltage across the resistor is just the product of those two things, and we end up with 10/3 of a volt. Okay, 3.333. So give me a moment. I'm going to go pull previous notes, but I think we're going to find that the Thevenin equivalent circuit was equivalent to the original. The Norton equivalent circuit was equivalent to the original. Guess what? They're equivalent to each other, and we're going to use that to our advantage in a moment. But let me go grab our previous analysis from one of the past videos. Okay, so the results match. Makes me feel like my memory's not completely gone yet. So from a previous video, we did the Thevenin equivalent for this circuit. And something seems to be corrupting my old images, which is very frustrating after I'm like, what, almost close to 100 videos done now. Hope those images are still alive. But we can see this was the analysis of the original circuit, and we found we had 2/3 of an amp and 10/3 of a volt. Okay, this was the analysis of the Thevenin equivalent. We had 2/3 of an amp and 10/3 of a volt, and that's what we got up here, right? So let's see. Now with the Norton equivalent, we match there, and with the Norton equivalent, we also match there. They're all equal to each other. All these circuits are equivalent to each other as far as the load's concerned. All right. So I'm going to do, hopefully you're comfortable with the idea that you already know how to find the Norton equivalent. Find I short circuit, and then find effectively our Thevenin, because that's also our Norton. Now you're going to draw it a little differently. It's a current supply with a parallel resistance, and then you hook up the load. But if it's truly equivalent, just like this one is, all of these results should match no matter which circuit you analyze. So pick which one you want to analyze. Okay, I'm going to do one more example like this just so that you see it again. A little repetition doesn't hurt. I'm going to throw a dependent supply in there. It's going to be a problem that we've already worked in the past. So it won't be new, but we're finding a different equivalent circuit. And then we're going to take a brief detour into something called maximum power transfer theorem, and then I'll teach you kind of a clever way to analyze circuits. Some people get stuck on it, but we're going to use Thevenin's and Norton's together to reduce circuits. Okay, so that's where we're headed. Stay tuned and good luck.